Hello students, in this video we are going to solve previous year JEE Mains and Advanced Chemistry questions related to the topic Haloalkanes and Haloarenes. I will solve each and every questions with explanation so that we can revise our chemistry concept. So let's start this video. The first question is the decreasing order of reactivity of the following organic molecules towards silver nitrate solution. So we should know that whenever we see the reaction of silver nitrate with halides, then it leads to the formation of carbocation and silver salt as silver halide precipitate out. Why is it so? Because silver ions has strong electronic ions has strong affinity towards halides. Therefore, it leads to the formation of the carbocation. So the rate of reaction will be directly proportional to the stability of the carbocation. And we know that tertiary carbocation is more stable than secondary carbocation and secondary is more stable than primary. But here all carbocation are secondary carbocation. So we have to see which one is more stable. So if you make the carbocation of this, it will be like this, and this carbocation positive charge delocalized due to the conjugation with the pi electrons. So this carbocation is stable. Now let's check this one. This is also stable because of the positive mesomeric effect of the methoxy group. So lone pair is in conjugation with this pi, and therefore this is stabilizing more effectively as compared to the A. So the most stable carbocation will be B and then A. Now let's look at this C. C will give secondary carbocation, and the secondary carbocation will be least stable as compared to the to A and B, because resonance stabilization dominates over plus I effect, and here you have only plus I effect of the methyl group. Therefore B is more stable and A is less stable than B, and A is more stable than C, and D is the least stable due to the presence of nitro group which has minus I effect. Hence the order of reactivity will be B, A, after that C and D, and if you see, this is matching to the option D. So the correct answer is D. Now the next question is, which of the following compounds will form the precipitate with aqueous AgNO3 solution most readily? So it means, as we discuss here, the formation of precipitate depends on the stability of carbocation. So we have to see that which carbocation is forming faster will give the precipitate faster, and that should be more stable carbocation. So these are the options. In option A, if you break this bond and put the positive charge, this carbocation is not stable. So for sure it will not give precipitate silver bromide. This is the precipitate which we are talking. So this precipitate will not form faster. Now let's see the option B. In option B, this carbocation positive charge will stabilize due to the presence of lone pair in conjugation with this empty p orbital of this carbocation, and it will give this stable carbocation. Now let's see option C. In option C is also this nitrogen lone pair is in conjugation with this positive charge, hence it is stabilized this carbocation also. And in option D, it is the same reason that positive charge stabilized by the lone pair of the nitrogen atom. So you can see that in B, C and D, in all the cases carbocation is getting stabilized, but now we have to find which one is the most stable carbocation. If you know that nitrogen and oxygen has more electronegativity than nitrogen, therefore tendency to give the lone pair for nitrogen will be more than oxygen. So this is the tendency of nitrogen to share its lone pair of electrons will be more as compared to the oxygen, and hence we can rule out that, hence we can see that carbocation B will be less stable than C and D. Now we have to choose from C and D. If you see that nitrogen of this compound lone pair is also in conjugation with the phenyl ring or benzene ring, it is in conjugation with the benzene ring, hence it is less available to stabilize the carbocation. But in case of D, the lone pair is not in conjugation with this ring and completely available for stabilizing the positive charge. Hence D will have more stable carbocation, therefore it will give more readily precipitate with this silver nitrate solution as silver bromide. So the correct answer is D. Now, among the following compounds, which one has the shortest carbon-chlorine bond? So shortest carbon-chlorine bond, we have to look which compound has partial double bond character. If you see in this compound, in this case you have only single bond character, single bond. In this case also, the lone pair of this halogen is not in conjugation with this pi. Therefore it is also has single bond character. Here is the same, but in this case the lone pair of the halogen are in conjugation with this pi bond. Hence here carbon and chlorine has partial double bond character. So therefore the bond length in option D will be shorter. So the correct answer is D. Now moving to the fourth question, the mechanism of SN1 reaction is given as. So let's understand this scheme. This is the alkyl halide, and alkyl halide break down to give carbocation and halides as an ion pair. Then after that, protic solvents play an important role to separate these anions, and after that, nucleophile attack to give the compounds. So in SN1 reaction, we know that carbocation is forming without attack of nucleophile. So you don't need strong nucleophile, and this carbocation has planar geometry. Therefore the nucleophile can attack from the front and from the back to give the racemization of the compounds. Now let's see what are the options. So the question is saying that the reaction is favored by weak nucleophiles, so we can say yes, this is correct. Carbocation would be easily formed if the substituents are bulky. Yes, because tertiary carbocation are more stable than secondary, and secondary is more stable than primary. The reaction is accompanied by racemization. This is yes, because carbocation has planar geometry, and therefore nucleophile can attack from back and front to give inversion and retention of the configuration, which leads to the racemization. The reaction is favored by non-polar solvent, so this is not true, because you need polar protic solvent to separate the ion pair. So we have to, which observations are correct? So first, second and third observations are correct, so therefore option C is the correct answer. Now let's move to the question 5th, the major product of the following reactions. So we have to understand that what is this reaction. This is the alkyl iodide reacting with tertiary butanol under high temperature. So tertiary butanol is not nucleophilic, because it is tertiary butyl is bulky. Therefore this reaction is not going to occur through nucleophilic substitution. So option D we can rule out. Now we have to see other options, and after looking at these options, it is indicating that the reaction is following either E1 or E2 elimination pathway. Since we don't see base in this reaction, therefore this cannot be E2 reaction. It means the reaction is following the E1 mechanism, and E1 mechanism, we know that first step is the formation of carbocation by the breaking of this carbon halogen bond, and after that we have to see that if there is a possibility of rearrangement to give more stable carbocation. So we can see that here there is a possibility that this hydride can transfer to this carbocation, and this is called 1,2 hydride shift, and to give the more stable carbocation. This is the more stable carbocation, this is tertiary carbocation, this was the secondary carbocation, now you have tertiary carbocation, and this tertiary carbocation has 2 beta hydrogen, one is here, and now we have to see which beta hydrogen will go away. So if you remove this beta hydrogen, then you get this product, which is least substituted double bond, and this is according to the Hofmann rule. And if you remove this beta hydrogen, then you get more substituted alkene according to Saytzeff rule. Now we have to understand which rule we have to apply here. Since Hofmann rule is applied when you have more acidic beta hydrogens. For example, if you see fluoro or N plus R3 group, in that case you have to apply Hofmann rule, otherwise you have to apply the Saytzeff rule. Therefore, formation of this product according to Saytzeff rule. Out of this, you can see the correct answer is C, not B. I hope this is clear to you. Now let's move to the question number 6. Which of the following compounds will show retention in configuration on nucleophilic substitution by hydroxide ions? So first option, in first case, you can see that this is the chiral center, because it is attached to 4 different groups: methyl, this is another alkyl, hydrogen, and bromide. So in this case, for sure you will get the either inversion of configuration or racemization. If it follows the SN1, then racemization, or if it follows the SN2, then you will get retention of the configuration. This is also chiral center, and in this case also this is benzyl halides, and in benzyl halides it can favor SN1 or SN2, both depending upon the conditions given for the reaction. So here if you will have the same problem, that you will not get the only retention in the configuration. Now let's see what other options are there. This is not chiral center, this is non-chiral. So if you attack here, nucleophile attacks here, so you will still get this non-chiral alcohol. So there is no discussion about retention or inversion of configuration, because the reactant itself is a non-chiral. Now let's see option B. In option D, we can see that this carbon is chiral, and what is the possibility here that these halides break down to give this carbocation, and then through rearrangement it gives more stable carbocation, tertiary carbocation, and after that this hydroxide nucleophile attacks to give this product. Now in this product, let's make it bond. If you see these two carbon are same, this is methyl, same methyl groups, hence it is non-chiral center, non-chiral. So if you see that the compound reactant was chiral, but product is a chiral. So in this case we can say that retention of configuration take place. So the correct answer will be D. For me this question is quite unclear, but we can explain only this way, that this was the chiral center and then you are getting non-chiral center, and hence the option D will be the correct answer. Now let's move to the question number 7. So the major product obtained from E2 elimination of 3-bromo-2-fluoropentane is. So first let's draw the structure. 3-bromo-2-fluoropentane. 1 2 3 1 2 3 4 5. So 2 fluoro. So fluoro, let's put here 2 fluoro and then bromo. Okay. So this is the structure of this given compound, and it is saying that undergoes E2 elimination. So what will be the major product? Now it is very interesting here, because E2 elimination involves removal of beta hydrogen by base, and simultaneously halides goes away. Now if you see, we have one this beta hydrogen, another this beta hydrogen, so we have two beta hydrogen. If you remove this beta hydrogen, then double bond will come. If you remove this beta hydrogen, then double bond will come. You are removing this, and then you have this. So if you see, so it is matching to which options? So this is matching to option C, right? It is matching to option C. But if you remove this beta hydrogen, then what will you get? Then you will have this product, and it is matching to which one? It is matching to B. So answer could be C or B. Now we have to understand which is major product. So as I discussed in the previous questions, that more acidic hydrogen, this is the more acidic hydrogen, due to the presence of this fluorine, which has very strong electronegativity, makes this hydrogen acidic as compared to this hydrogen. Therefore this hydrogen present at the fluorine carbon will remove first and give the product according to the Hofmann rule. Hence B will be the major product. So the correct answer is B. So moving to the question number 8. Consider the reaction sequence given below. So the first reaction, this one is the example of SN1 reaction, and the rate is depending on the reactant concentrations, not on the concentration of the base. And the second one is, after looking this formula, we can say that rate of the reaction is depending on the concentration of reactant and base. Therefore this reaction is following E2 pathway. Now which of the following statement is true? Changing the base from hydroxide to alkoxide will have no effects on reaction 2. So this is not true. It is a false statement, because if you change from hydroxide to alkoxide, then this elimination of the proton will be faster, and therefore it will have for sure the effects on reaction 2. Now changing the concentration of base will have no effects on reaction 1. So if you see, the rate of the reaction depending on the concentration of reactants, not on the base. Therefore the statement B is correct. Let's see what is option C. Doubling the concentration of base will double the rate of both the reactions. So actually doubling the concentration of base will double the rate of the reaction for only reaction 2, because in this case you can see that it depends on the concentration, but not for the reaction 1. Therefore statement 3, this is false. Now changing the concentration of base will have no effects on reaction 2. This is also false, because as we see that if you change the concentration of base will have effects on the reaction 2. So this is also false statement. So the correct answer is B. This is the correct answer. Now moving to the reaction number 9. The decreasing order of reactivity towards dehydrohalogenation following even mechanism for the following compounds. So we know that even reaction follows carbocation pathway. Carbocation. Therefore, rate of even reaction directly proportional to the stability of carbocation. So we have to see which carbocation is more stable. So let's start from here. So this will give you primary carbocation. And if you see here in case of B, so you will have after breaking this bond, the positive charge will come here, and then this hydride shift will bring the positive charge at allylic position, and these allylic carbocations are more stable due to the conjugation of these pi electrons, and allylic carbocations are more stable than secondary carbocation. Okay, so now let's see the option C. This will give secondary carbocation, and this will directly give you allylic carbocation. And allylic carbocation is more stable than secondary carbocation. So among B and D, the most stable carbocation will be given by D. So in option A, there is only one option in which D is at the highest. Okay, so let's see which one the least one. So A will be the least stable carbocation, and which is in the end. Therefore, the correct answer is A. And you can also see that after D, the stability of the carbocation B is more as compared to secondary carbocation. So without any doubt, the correct answer is A. Now moving to the next question, consider the following reactions. So this is the dehydration reaction. This is elimination reactions because you have alcoholic KOH, strong base, and the reaction third is also elimination reactions. And fourth, actually in fourth, the correct formula is this is something is missing here actually. So I want to write the correct one, CH3 to CHOH. So this is the correct structure of this compound. Okay, so we have to see which of the reactions will not produce Saytzeff product. So Saytzeff product is that product which gives more substituted more. Okay, so let me write this structure, open structure of all these molecules. Okay, so I have wrote the structure. So in the first case, if you see this hydroxy will undergoes removal of water and give the carbocation, and this carbocation will get stabilized to the tertiary carbocation, and after that this proton will go away and it will give the more substituted alkene. And in case of reaction 2, if you see alcoholic KOH is a strong base, so therefore it will abstract this beta proton. So after abstraction of this beta proton, you will have more substituted alkene. This will be the product, and this is according to the Saytzeff. So this is the more substituted alkene. Now let's look at the option 3. In option 3, you have two beta hydrogen. One is this, and another is from this methyl. But since this tertiary product site is very hindered base, this tertiary product site is a hindered base, due to which this will not be able to abstract this proton, not possible because of the steric crowding here, steric crowding and bulky base. Therefore it will prefer to abstract the proton from this place and give the less substituted alkene, and this is Hofmann product. And now look at the last option, fourth. In the fourth case, it will undergoes dehydration of the water on heating, if you remember the aldol condensation reaction. So this is beta hydroxy, and beta hydroxy undergoes elimination of water molecules and gives alpha beta unsaturated carbonyl compounds, and this is also more substituted one. And this is also follow the Saytzeff according to the Saytzeff rule. Hence the correct answer will be 3. Only 3 will give Hofmann product and not Saytzeff product. Question 11. The major product of the following reaction. Okay, so this is dihalide, 1,2-dihalide. Whenever you see 1,2-dihalide reaction with alcoholic KOH and after that soda amide in liquid ammonia, then it leads to the formation of alkynes, triple bonds will come. And so if you see in the given option, the correct answer will be D. And the mechanism is as follows. For abstracting this proton, you need a very strong base, and soda amide is very strong base. So therefore it will abstract this proton, and removal of the HBr will give you this triple bond. Now moving to the next question, which hydrogen in compound E is easily replaceable during bromination reaction in presence of light? So bromination reaction in presence of light is the example of radical reaction. So this bromide radical will form. So we have to see which hydrogen removal will give the stable radical, and we know that allylic radical is more stable than vinylic radical due to this resonance, and this radical delocalized to other position. Therefore, hydrogen at C will easily replaced. So the correct answer is C. Now moving to the question number 30, the major product of the following reaction. This reaction is very difficult and very interesting, and believe me, you have to think in every aspects. You need very great knowledge of SN1, SN2, E1, E2 reactions. So we will think in all the possible ways. So imagine that sodium methoxide is attacking below the plane, then it leads to the formation of this product and through SN2 mechanism, and this is matching to D. Okay, we can also think that this reaction can follow SN1 pathway. So if we follow SN1 pathway, then first it will form the carbocation, after that stabilization of the carbocation by migration of this methyl group, and then removal of this proton to give alkene. So this is matching to option C. Now let's think another possibility, that this is a strong base. Sodium methoxide is a strong base and it is abstracting this proton from the beta position, and this is anti-periplanar, and after abstracting this proton, at the same time removal of the halogen gives alkene through E2 mechanism. Now option A we can easily rule out. So there is this product cannot be have retention of the configuration. Okay, inversion is possible through SN2 mechanism. Okay, now let's think about which possibility we should rule out. Since this is very strong base and this is secondary carbocation, so you can think about SN1, but due to strong base we can rule out SN1 pathway because of the presence of the strong base. Now two possibility left, E2 mechanism or SN2. For SN2 you need nucleophile should approach to the halides carbon, but if you see this is 4 substituted 4 substituted carbon, and here it is secondary carbon. Therefore this presence of the big methyl group is hindered the approach of the nucleophile, and hence it rules out the possibility of this SN2 product. Now what is left? E2 elimination. E2, yeah, this is the only options left. And why? Because this hydrogen, there are two hydrogen, one is anti-periplanar to this bromo, and removal of this hydrogen through this strong base lead to the formation of this alkene. So the correct answer is B. So again I am saying why it is following E2 pathway, because of the strong base and steric hindrance at beta position prevent the SN2 pathway. So that's why the correct answer is B. Okay, so the next question is, which of the following will most readily give the dehydrohalogenation product? So dehydrohalogenation product are possible in E1, E2 and E1CB reactions. So but the given reactions, if you see the given substrates have vinylic beta proton and vinylic beta hydrogen. Therefore vinylic, if you remove the vinylic beta hydrogens, then it will give the carbon ion. So we can rule out E1 and E2 possibility. So all these substrates will follow E1CB mechanism, and in that case carbon ion will be intermediate. Now we have to see that which will give more stable carbon ion. So after removal of this, negative charge will come here, and this negative charge will delocalize over this vinyl ring, can easily delocalize over this vinyl ring to stabilize this negative charge. In this case also negative charge can stabilize through the sp2 negativity of this carbon, and through the resonance also. If you see here, this removal of this proton will give negative charge, and this will only stabilize through the sp2. So there is a resonance stabilization, here is also resonance stabilization, but in this case only stabilization through the electronegativity. And now what is going to happen here? In this case you will have, after removal of this proton, you will get benzene, and benzene is it is highly reactive. So out of this, which one is giving the most stable carbon ion will react faster. So the option A is the correct one, because in this case carbon ion is stabilized through this phenyl ring as well as conjugation with this double bond. But in this case stabilization is only less number of resonating structure as compared to A. So in A is more stabilization than B. Hence the correct answer is A. Now moving to the question number 15. Which of the following reagent is not suitable for the elimination reaction? First reagent is sodium iodide. If you remember that reaction of alkyl halide with sodium iodide leads to the replacement of the halides by iodide, and this is known as Finkelstein reaction. And rest of the cases, in remaining cases, this is the base. This is ethoxide base, hydroxide base, and this is also hydroxide base, and it can easily remove this beta hydrogen, leads to the formation of alkene, and hence the correct answer will be A. So A, sodium iodide, will not lead to the elimination of the reaction. Now moving to the question number 16. The synthesis of alkyl fluorides is best accomplished by Finkelstein reaction? No, as we have already seen, this Finkelstein reaction involves the reaction of alkyl halides with sodium iodide. Schwarz reactions, yes. In Schwarz reactions, we use the reaction of alkyl halides with fluoride, source of the fluoride, such as this or antimony fluoride, to give alkyl fluoride. Free radical fluorination, no. Sandmeyer reaction, no. Sandmeyer reactions involve the diazonium salt formation, and then attack of the nucleophile. So this one no, this one no. So the correct answer is B. Now 17. In SN2 reaction, the correct order of reactivity of the following compounds. So SN2 reactions follow. Primary is alkyl halides is more reactive than secondary and then tertiary. So we have to see the correct option. So if you see, this is the CH3 should be first. So in which cases here is CH3 is first position, CH3 methyl is first. So out of these two we have to choose, and then this is the primary, and here is the secondary, and then after that secondary, and then tertiary. So the correct answer will be B. Now moving to the next. For the compounds, this the correct order of increasing carbon halogen bond length. So carbon halogen bond length. So if you see this down the group from fluorine to iodo, size of the atom increase. Therefore, the size increase in the size, the bond length is also increasing. So carbon iodide bond length will be more than carbon bromide, and so on. So the correct answer will be first A. A will be the correct answer. Now the order of reactivity of given haloalkanes towards nucleophile is order of reactivity. So this we can explain in two ways. First, by using the concept of good leaving group. So we should know which is the good leaving group. Iodide is better leaving group than bromide, and bromide is better than chloride, and chloride is better than fluoride. Because of the big size of the iodide, the negative charge gets dispersed. Okay, so the correct order, so therefore the reactivity towards nucleophile will follow this order. And we can also explain through the bond energy. Carbon iodide will have lower bond energy as compared to carbon bromide, and carbon chloride, and then carbon fluorine, because of the small size of this bond. This will be more difficult to break. Therefore bond energy is increasing in this order, and therefore reactivity is also decreasing in this order. Okay, now moving to the question number 20. This question is very important, so let me remove this all those things. Okay, this question 20 question reaction is very important. So it is asking potassium iodide in acetone undergoes SN2 reaction with each of these molecules P, Q, R, and S. The rate of the reactions vary as. So what will be the rate of the reaction? So we know that potassium iodide in acetone follow SN2 pathway. Following the SN2 pathway, so now we know that primary alkyl halides reacts faster than secondary alkyl halides, and then tertiary. So here we can see that P is the primary. Sorry, this is 0. It's not even primary. So this should react faster as compared to Q, because this is secondary, and this is allylic. This one is allylic. But here is very interesting molecule. Which is S. This is alpha haloketone. We should understand the reactivity of alpha haloketones. If you see these alpha haloketones, then without thinking anything, understand that this has very high reactivity as compared to primary. Alpha haloketones has very high reactivity. Haloketone has high reactivity as compared to primary alkyl halide. We should understand these things very clearly. Why is it so? There are two reasons. First, this carbonyl group is electron withdrawing group, and therefore This creates the partial positive charge at the alpha carbon. So partial positive charge positive at alpha carbon. So increase the electrophilicity of this. And second reason, in SN2 mechanism, transition state has negative charge and carbonyl group is electron withdrawing group, therefore stabilize the negative charge. Therefore reactivity of S will be higher. And then now which one will come second, P or R? Look, it is very interesting. If you have primary alkyl halides, then for sure allylic will be more reactive. Allylic halide will be more reactive, but you have zero directly connected to this, so that's why P is more reactive than allylic halides. And secondary is of course coming at the end. So which is the correct options? So the correct option is B. Luckily in this case only one option has in which case they are showing the S has higher reactivity. So once you find this, then you are all set. But imagine if you have one more options with the S, then it could be a problematic. And we have to be very careful between primary alkyl halides and allylic halides. Allylic halides are more reactive than primary alkyl halides because of the sp2 nature of this part stabilize the negative charge during the transition state of the SN2 reaction. Okay, now moving forward, the reagents for the following conversion. So we have already seen before. So this is the vinyl dihalide. So alcoholic KOH, yes, alcoholic KOH can remove one of the halides, but after that to get this one you need soda amide. So this one alcoholic KOH followed by soda amide. Yes, this is the correct answer. Aqueous KOH followed by soda amide. No, because aqueous KOH is a strong OH, is a strong nucleophile. So it will lead to the substitution reaction. Substitution rather elimination. So therefore this is not the correct answer. What is the fifth? Zinc assay. Zinc in. No, this is reducing agent. Okay, now moving to question 22. What would be the product formed when 1-bromo 3-chlorocyclobutane reacts with the 2 equivalents of metallic sodium in ether? So we should know first to make this kind of species. So let's draw the structure of this. Okay, so let's say this is bromo 1 3, this is chloro. So first bromo will cleave to form sodium and it will have partial negative charge. If you remember, this is the example Woods react. First it will remove the bromide and then this carbon ion undergoes nucleophilic attack, intramolecular nucleophilic attack, and gives this kind of product. So correct answer is D. Identify the set of the reagents reaction condition X and Y in the following sets of reactions. So look, first this is the alkyl halide and then X giving the product, and after that this. So for sure this product having double bond. To get this double bond, and we need strong base, not nucleophile. We need the base to create the double bond. So let's look the option 1. A, dilute aqueous sodium hydroxide. So it will be a nucleophilic. So it will lead to the substitution. It will favor the substitution, not elimination. Let's look the option B. Concentrated alcoholic NaOH. Yes, alcoholic NaOH will give this kind of base, and this is the strong base with low nucleophile favors elimination over substitution. And now let's look the B, HBr acetic acid. Yes, this looks to me correct answer. Let's look what is written further. Dilute aqueous NaOH. No, this is no. And then alcoholic NaOH. Okay, the first is correct. This first part is correct, but what about the second part? Okay, in the second part they are giving the bromine. So if you have this product and if you react with the bromine, then it will lead to the bromination and both the double bond, and it will give you this dihalides. So therefore option D is incorrect. So option B is the correct answer. Now, a solution of 2-chloro-2-phenylethane in toluene racemized slowly in the presence of a small amount of antimony pentachloride due to the formation of. Okay, so if you see that 2-chloro-2-phenylethane, this is benzylic halide. So what will be the intermediate? So for sure this will break down and it will lead to the formation of the carbocation. And carbocation, in the case of carbocation, has planar geometry, and therefore it will attack by both sides and leads to the racemization. So the reaction follow the carbocation intermediate. So correct answer is D. Now 25. So this is Grignard reagent reaction with the D2O produces. So Grignard reagent easily get proton from the acidic medium. So what will be the product? CH3 3CMg. So Mg will break down and hydrogen, it gives the hydrocarbons. So since we have deuterium, so it will catch the deuterium. So this should be the correct answer. Let's look other options. CH3 COD, no. This no. This cannot be answer. Other deuterium, no, it will not go to the places, no. So the correct answer is A. Okay, now let's move forward. Reaction number 26. Isobutyl magnesium bromide. Isobutyl magnesium bromide with diethyl ether in ethyl alcohol. So again, it will take the proton. So isobutyl will take the proton to give the hydrocarbon, and ethyl alcohol will goes to the magnesium side. So let's check. This is OH. No, this is not the correct answer. So B. In case of B, yeah, this is the correct answer, because you can see that this is producing the hydrocarbon, and ethyl alcohol is going to the magnesium alkene. This is no, and this first part is correct. This is not the correct answer, because this anion part you have to show in the bracket. So this is not the correct answer. The correct answer is only B. Now the chief reaction product of reaction between N-butane and bromine at 130 degrees Celsius. So N-butane and bromine. So bromine will decompose to give Br radical. So, and the Br radical, and the secondary radical is more stable. Radical is more stable than the primary radical. Therefore, the product will be not this, and in this case, this dibromination is taking place, not this one, and the same, not this one. So this will lead to the monobromination, and correct answer is B. Okay, now moving to question number 28. 1-chloroputane on reaction with alcoholic potash gives. So alcoholic potassium, it will lead to the formation of butene through elimination reaction. So this will lead to the formation of 1-butene, because this CH2 alcoholic C2H5 hydroxide, this is a strong base and weak nucleophile. But in case of aqueous KOH, in this case you will get alcohol by the substitution of this halogens. But here the reaction is following A2 mechanism. Question number 29. This question is very important. So HBr addition to 2-pentyne. So let's draw the structure of 2-pentyne. Okay, so this is the structure of 2-pentyne on reaction with HBr. So there is a possibility that the proton can go at this or at this. So CH3, one is this, and second is, okay, so 1 and 2 are two different structural isomers. And now if you see this around this double bond, this substituents and this substituents are different, so they will show E and Z geometrical isomerisms. And similarly here it will show you geometrical isomerism E and Z. So therefore there are four geometrical isomers and 2 structural isomers. So 2 structural isomers and 4 geometrical isomers. So configurational isomers, we should know that configurational isomers is into 2 categories. One is geometrical, another is optical. So there is no chiral center, so therefore there is optical isomerism is not possible. Only geometrical isomerism is possible, because double bond dead carbon have different substituents. So the correct answer is B. Okay, now question number 30. N-pentyne bromide on treatment with ethanolic potassium hydroxide products produces. So you can see that ethanolic potassium hydroxide and propyl bromide. So here is the again it will lead to the elimination propene through E2 reaction. So the correct answer is D1. The reaction condition leads to the best yield of C2H5 chloride. Okay, so in the first reaction, C2H6 reacted with excess of C2H6 reacted with chlorine. So you will have H5 chloride. In this case, also dark room temperature, you will not get the product. And in this case, chlorine is in excess, so you can have monochlorinated, and you can also get dichlorinated product, because chlorine is in excess amount. So you will have more products, and in this case you will like this is also will give you this product. But the question saying gives the best yield of C2H5 chloride. So in these 2 cases we can easily rule out. Now we have to choose out of this A and D. So in this case of A, you have reactant, it is in excess amount. So this excess amount of reactant will avoid the overchlorination, and then you will have more amount of the product, but in this case you can have mono and dichlorination also. Therefore the best yield of desired product will be in case of A. Hence the correct answer is A. Among the following compounds, the most acidic is para-nitrophenol, para-hydroxybenzoic acid, ortho-hydroxybenzoic acid, para-toluic acid. So let's draw their structure first. Okay, so you can see that without any doubts, we know that carboxylic acids are more acidic than phenol. So we have to choose the answer from B, C, and D. In case of B, the hydroxy is at para position, and this hydroxy have plus mesomeric effects and hence increase the electron density on this carboxylic group and decrease the acidity. In case of orthohydroxy is the same, but after removal of this proton, the negative charge carboxylate is stabilized through the hydrogen bonding, and hence this becomes stronger acid as compared to para-hydroxybenzoic acid. Now in coming to the toluic acid, in this case also methyl has plus I effects and hence increase the electron density over this carboxylic group. Therefore we can clearly say that the most acidic compound is ortho-hydroxybenzoic acids. But suppose if we have to arrange them in decreasing order of their acidity, then C will be more stronger acid. After that D, toluic acid, because in toluic acid only inductive effect is there, which is increasing the electron density and which is poor as compared to mesomeric effect. And then para-hydroxybenzoic acid, and the least acidic is A, para-nitrophenol. So ortho-hydroxybenzoic acid is the strongest acid, then para-toluic acid, and after that para-hydroxy, and then para-nitrophenol. The number of stereoisomers obtained by bromination of trans-2-butene is, so how many stereoisomers you will get on bromination of trans-2-butene? This question is very important. So this is the structure of trans-2-butene. We should remember that bromination gives anti-product, anti-addition. Bromination is a anti-addition, and therefore it leads to the formation of meso compound, optically inactive compound, and hence only one stereoisomer will form. So the correct answer is A. Here I would like to take your time to explain you something more interesting things. The best way to remember that whether you will get meso compound or racemic mixture, I use this analogy, mathematical analogy. For example, if you have trans alkene and this addition reaction on this double bond is anti, let's say it is trans. So I use this mathematical analogy, trans geometry minus trans addition gives 0. 0 means no optical rotation, optical rotation is 0. And which compound has optical rotation 0? Meso compound. But now imagine you have trans geometry and the reaction is with osmium tetraoxide, which is syn. Let's call syn cis. So in this case I use my mathematical analogy, trans minus cis addition, trans geometry minus cis addition gives non-zero. Hence you will get racemic mixture. So here you will have dihydroxylation, syn dihydroxylation, but it will be racemic mixture plus minus. But if you have cis geometry, in this case cis addition will lead to the formation of meso compound. I hope it is clear to you. Let's move forward. Question number 34. Okay, you can see that this is alkyl chloride and secondary 1, 2, 3 tertiary halide. What is the question? So the question is this compound on hydrolysis in aqueous acetone gives what? So we should understand that this reaction will follow SN1 pathway. So you will get tertiary carbocation. Okay, so let's make the tertiary carbocation from this how it will look. This is tertiary carbocation, and this carbocation can get further stabilized because this hydroxy can go, this hydrogen can go 1 to shift to give the carbocation here. Okay, now there is another possibility that this methyl can go here and positive charge comes here. So if positive charge comes here, and so one is intermediate, this possible, and second intermediate is, but this carbocation is unstable unstable due to electron withdrawing nature of this nitro group. Hence, this more stable carbocation. This is the more stable carbocation, benzylic carbocation. This is the benzylic. This is the most stable carbocation due to the positive mesomeric effects of this methoxy group. It is stabilized the positive charge here. So now we can see that there is a possibility of formation of product 2. This product 3 will not form. This product hydroxy will not come at this position because it is unstable. And what about 1? In first case, this is the substitution is taking place directly by the removal of the chloro. So this is also possible, but this one is not possible. So let's see, mixture of 1 and 2. Yes, it is possible. Mixture of 1 and 3, no. Only 3, no. Only 1, no. So we can say that correct answer is A, mixture 1 and 2, because 3 cannot form due to the unstable or carbocation by electron withdrawing group present on this benzene ring. Now moving to the next question, which of the following compounds exhibits stereoisomerism? Stereoisomerism: 2-methyl butene, 3-methyl butane, 3-methyl butanoic acid, 2-methyl butanoic acid. So we have to draw the structure of each compound. Okay, so these are the structures of given options. So if you see 2-methyl butene, there is no geometrical isomers because the substituents at this carbon are same hydrogens. So it will not show no geometrical isomerisms. If you see here, this carbon is not chiral because it has same methyl group. Now let's move forward. In case of 3-methyl butanoic acid, this you have same substituents on this carbon, so no chiral center, no chiral. Now let's look at this. So we have one substituent ethyl, another is methyl carboxylic group and hydrogen. So this is the chiral center. Therefore, it will show 2 optical isomers, and the correct answer is D. Moving to reaction number 36. An SN2 reaction at an asymmetric carbon or compounds always gives an enantiomer of the substrate. No, because substrates and products have different configuration, and we know that inversion of configuration take place. Inversion. A product with opposite optical rotation, it is not necessary. May or may not. So product may have same optical rotation or may be different from the reactants. So this is also not possible. A mixture of diastereomers. This mixture of diastereomers is possible when there is one more chiral center. So if there is only one chiral center, then you will get the enantiomers only. So this is also not possible. A single stereoisomers, yes, and that in single stereoisomers is the inverted product, inverted configuration. So the correct answer is D. The order of reactivity of the following alkyl halides for a SN2 reaction. So order of reactivity depends on the stability of leaving group. Iodide is more stable as compared to bromide, or we can say that iodide is better leaving group as compared to bromide, and so on. Therefore, the order of reactivity will be alkyl iodide will be more reactive than alkyl bromide, and alkyl bromide more reactive than alkyl chloride, and so on. So the correct answer is D. Now, which of the following has highest nucleophilicity? So nucleophilicity depends on electron density and size of the nucleophile. If nucleophile is bulky, then its nucleophilicity will be lower. But here, if you see that sizes are comparable, so what we have to see, electronegativity of donor atom. So chlorine is more electronegative than oxygen, and oxygen is more electronegative than nitrogen, and nitrogen is more electronegative than carbon. Therefore, the carbon will have more tendency to give its electrons dense. So carbon will have highest nucleophilicity because it's so the correct answer is C. How many optically active stereoisomers are possible for butane 2,3 diol? So butane 2,3 diol structure is this one, and there are 2 chiral centers. So we can use this formula, 2 number of chiral centers, so 2 power 4. So 4 stereoisomers are possible, but the substituents are same. Therefore, in this case, the formula becomes 2 raised to power n minus 1. So therefore, answer will be 3. So it will have 3 optical isomers, and you can draw those 3 optical isomers. First will be this. Second, you can draw OH here, and this one second, and third will be its mirror image. So in reaction 40, the bond angle, it is asking the bond angle. So this has sp2 hybridized and it is sp3. So bond angle in sp3 case is around 109 degree and in case of sp2 is around 120. Therefore, the correct answer is A. Question number 41. For the given compound X, the total number of optically active stereoisomers is. So what is X? Let's see. So this is the compound and they are saying that this bond indicates that the configuration at the specific carbon and the geometry of the double bond is fixed. Okay, so we can see that this hydroxy is above the plane, this is also above the plane, and this is also above the plane, and the configuration at this carbon is also above the plane with the trans geometry. And they are saying that this bond, which is wavy bond, configuration at the specific carbon and the geometry of the double bond is not fixed. So this configuration, whether it is cis or trans, it is not fixed, and the chiral center configuration at this chiral center is also not fixed, and same hydroxy. So we have to think how many possible stereoisomers it can have and how many of them are optically inactive. So if you see that at this double bond we can have two possibility, one is trans and another is cis. And in case of trans, there is a possibility that this hydroxy, let's say first, let's label this carbon at this, let's say this carbon is first and this carbon is 2. So the configuration at C1, C2, let's say it is above the plane, and hydroxy is also above the plane, OH is also above the plane. So one possibility is this one, and another possibility with this is that C1 and C2 is above the plane, but hydroxy C1 C2 above the plane, but hydroxy is below the plane. Okay, so these two possibilities are there, and then what else is there? Now in these cases we taken C1 and C2 above the plane. Now let's take below the plane. So C1 and C2 below the plane, this bond is below the plane. Then there is a two possibility that OH above the plane and below the plane. So how many possibilities are there? So one is this, second this, third is this, and fourth is this one. So with the trans geometry we can say that 4 stereoisomers are possible, 4 stereoisomers. And if you see carefully, when this double bond has trans configuration and it is above the plane, it means this, in this case, above the plane, and hydroxy is also above the plane, then it has plane of symmetry. So therefore one is optically inactive. So out of 4, 3 are optically active and 1 is optically inactive. So similarly, for cis configuration at this double bond, 4 stereoisomers are possible, and in this case all are optically active, because there is no plane of symmetry, so we can easily see that there is no plane of symmetry when you have the configuration at this double bond cis. And the similarly 4 stereoisomers are possible as we have described for the trans. So 4 and 4, 8 isomers, but one of them is optically inactive, and they are asking how many optically active. So optically active, how many? 7 are optically active. So the correct answer is 7. Question number 42. In the following monobromination reaction, the number of possible chiral products is. So first we have to understand this reaction is radical reaction, and radical reaction is not selective. It can go and replace any hydrogen. So we have to draw all possible compounds with only monobromination, and we have to see which of them has plane of symmetry. So we have to draw Fisher projection. If we draw the Fisher projection, then it will be easy to understand which one is chiral and which one is achiral. If you see plane of symmetry, we know that if the compound has plane of symmetry, then it is achiral. If no plane of symmetry, then it is chiral. So let's draw all possible products of monobrominated for this compound. Okay, so these are the possible monobrominated product of this given compound. So let's we label the numbering 1, 2, 3, 4, 5 to each carbon. And first we are drawing the product by brominating the methyl one, and you can see there is only one chiral center, and this compound doesn't have a plane of symmetry, so it is chiral. Now another product in which bromination is going on this carbon 2, let's say carbon 2, and in this case if you see that this carbon is not asymmetric because it has same substituents, so this is achiral. Now the third product is possible by brominating the third carbon, and this gives chiral center. Therefore there is a possibility of its diastereomer, so the bromination can go on the other side to give diastereomer. So these are diastereomer of each other, and if you see that there is no plane of symmetry, this molecule doesn't have plane of symmetry, so therefore this is chiral, and this one is also chiral. Now let's see the third 1 2 3 4, so this is the fifth one. So in the fifth product is possible by the brominating the fourth carbon, and this is also generating the chiral center, so therefore another bromination is possible on the other side, so this one. Now look at this compound, it has plane of symmetry because bromo are on the same side, therefore it is achiral. But this compound, this doesn't have plane of symmetry, therefore it is a chiral compound. Now the last one is forming by the bromination at fifth carbon, and this is not chiral, therefore only one possibility is there. And if you see there is only one asymmetric carbon, therefore this is also a chiral compound. So how many chirals are there? 1 2 3 4 5. So the correct answer will be the number of possible chiral products 5. Question number 43. The total number of alkenes possible by dehydrobromination of 3-bromo-3-cyclopentyl hexane using alcoholic KOH. So first we should draw the correct structure of 3-bromo-3-cyclopentyl hexane. Okay, this is the structure of 3-bromo-3-cyclopentyl hexane, and now on treating with alcoholic KOH, it undergoes elimination reaction. So we have to see how many beta hydrogens are there. So one beta hydrogen is here, one is beta hydrogen is there, let's call it H2, this one H4, and let's call this one 3. So when you remove hydrogen 2, then you will get this product 1 2 3 4 5 6. And if you see that the substituents around this double bond, so this is hydrogen, this is methyl, and substituents at this carbon, double bonded carbon, are different, so it can show E and Z geometrical isomers. Okay, let's remove hydrogen 4. If you remove hydrogen 4, then you will have this product. And in this case also, you can see that this double bonded carbon has different substituent. This one is hydrogen, this one is ethyl, this one is ethyl, and this is cyclopentyl. Therefore, it can also show EZ geometrical isomers. Okay, now let's remove proton 3. If you remove proton 3, then you will have this structure. And if you see, the substituents at this double bonded carbon are same, and here 1 2 3 4 5 6, here one is ethyl, another is propyl. These are different, but this is same, so it will not show EZ is not possible in this case. It will show only one isomer. Hence total isomers are 2 from this structure, 2 from this structure, 1 from this, so total 5. Therefore total number of alkenes possible by dehydrobromination 5. Answer will be 5. Question number 44. The total number of monohalogenated organic product in the following including stereoisomers reaction is, so what they are saying, simplest optically active alkene, we have to take simplest optically active alkene. And then first reaction is hydrogenation reactions. It means this alkene will give hydrocarbons. And second is halogenation reaction. Okay, so let's take the simplest alkene. So first we will draw alkene. Okay, we can't draw optically active alkene with 2 carbons. So let's add one more carbon. Still we can't make it. So let's add methyl and then ethyl. So now you can see that this is asymmetric carbon. So this is the simplest optically active alkene. First reaction was the hydrogenation reaction. So hydrogen will add to this double bond and will give saturated hydrocarbon. Now you can see that this carbon is no longer asymmetric carbon because it has same substituents or same group on this carbon. So the next step is halogenation reaction in the presence of light. So this is following the radical pathway. So we have to draw all monohalogenated products. So we have to replace hydrogen from each and every carbon and draw all possible products. So first possibility is this one, and this is not non-chiral. So only one possible. This is the second one. Now look at this structure very carefully. After monohalogenation, this is chiral center because it has 4 different group, and this is also chiral center. So there are 2 chiral center, therefore it will have 4 stereoisomer. And the last possible product is this one, in which halogenation is going at the terminal carbon. Now you can see that after monohalogenation at this carbon becomes asymmetric. Therefore it has 2 stereoisomers which are D and L. So how many total? What was the question? Question was monohalogenated organic products, stereoisomers. We have to include the stereoisomers. So how many are there now? So 4 from this because it has 2 chiral center, 2 from this, 6. 1 is from this because it doesn't have any chiral center. So 1 from this and 1 from this. So 4 to 6, 7, 8. So answer is 8. Question number 45. Vinyl chloride on reaction with dimethyl copper gives. The dimethyl copper structure is this one. Remember, whenever carbon bonded to a metal, it always carries negative charge because metal has electropositive character and therefore it increases the electron density on the carbon. Hence, it can act as a nucleophile. Now, it reaction with the vinyl chloride. So, when it will react with vinyl chloride, then copper chloride will go away and methyl will come here to give CH2 double bond CH and CH3. Question number 46. The interaction of elemental sulfur with Grignard reagent gives what? So when elemental sulfur reacts with Grignard reagent, it gives R, S, and then salt formation followed by hydrolysis to give thiol. So it will give thiol. Next, isomers which are mirror images are known as. So what will be there? Non-superimposable mirror images are known as enantiomers. So non-superimposable, here you will fill non-superimposable mirror images are known as enantiomers. But diastereomers are non-mirror images. Diastereomers are those stereoisomers which are non-mirror images, means they don't have mirror image relationship. Okay, so here we will fill non-superimposable and this will be enantiomer. Next, the compound prepared by the reaction of magnesium with diethyl bromide in ether is known as, so this is very simple, Grignard reagent. The halogen which is most reactive in the halogenation of alkanes under sunlight. So reactivity order is this: chlorine is more reactive than bromine and bromine is more reactive than iodine. Iodine is almost unreactive. Therefore the correct answer is chlorine. Now true and false. 2, 3, 4 trichloro pentane has 3 asymmetric carbon atoms. So let's draw pentane 1, 2, 3, 4, 1, 2, 3, 4, 5, and 2 has chloro, 3 has chloro, and then 4 has chloro. So if you see, this compound has plane of symmetry. When the compound has plane of symmetry, then it is optically inactive. So, but he is asking how many asymmetric carbons are there. So it has one asymmetric carbon and two asymmetric carbon. This is not asymmetric carbon because the attachment at this is, one is this, second is this, and which are same, and third is hydrogen, fourth is chlorine. But this attachment and this one are same, therefore it has only two asymmetric carbon. During SN1 reaction, the leaving group leaves the molecule before the incoming group is attached to the molecule. Yes, it is true, because in SN1 reaction, first alkyl halides undergoes decomposition to give ion pairs, and in ion pairs, one is carbocation without the attack of nucleophile. So therefore, this statement is question 52. The reaction of vinyl chloride with hydrogen iodide to give 1 chloro, 1 iodoethane is an example of anti-Markovnikov's rule. So vinyl chloride with hydrogen iodide. This is the structure of vinyl chloride reacting with hydrogen iodide. According to Markovnikov's rule, hydrogen should go to the carbon having more number of hydrogen atoms, and iodide goes other carbon, double bonded carbon. So this is the product according to the Markovnikov's rule. So what is saying that 1 chloro, 1 iodoethane is an example of anti-Markovnikov's rule? No, this is false statement. This is the example of, because this is 1 iodo, 1 chloro, ethane. So therefore this is following the Markovnikov's rule, not anti-Markovnikov's rule. Now iodide is a better nucleophile than bromide. Okay, so here it is very interesting to note that iodide is better nucleophile than bromide in protic solvent, because in protic solvent bromide will get solvated more as compared to iodide. So therefore iodide is a better nucleophile than bromide, and this is true statement, but actually it is not very clearly mentioned. And if this question was in a non-polar, let's say non-polar or non-protic solvent, then this will be false. So here the question for me is not very clear, because iodide is a better nucleophile when you are talking in a protic solvent medium, but when you are talking in a protic solvent, then bromide is better nucleophile than iodide, because in case of iodide, electron density get dispersed, and hence its nucleophilicity decreases as compared to bromide. But we have to also consider the solvent effects. So therefore this question is quite unclear to me, because it is not fully described. But you should remember that this is the order of nucleophilicity when you are talking about protic solvent, and when you are talking about a protic solvent, then bromide better nucleophile than iodide. Now moving to MCQ with one or more than one correct answer. So now this question number 54 can have one correct answer, or it can have more than one correct answer. So what is the question? For the following compounds, the correct statements with respect to the nucleophilic substitution reactions are. So this is benzyl bromide, and this is alkyl bromide. This is tertiary halide, and this is secondary benzyl halide. To answer this question, we should recall some important fact. First important fact is that benzyl halide and allylic halides can show both SN1 and SN2 mechanism. Why? Because we know that carbocation is stable in above cases. So we know that benzyl carbocation and allylic carbocation are stable. Therefore, it can show the SN1 pathway and SN2 pathway, because in case of SN2 pathway, the negative charge in the transition state is stabilized by electron withdrawing nature of phenyl and allyl, because it has sp2 carbon, so it stabilizes the negative charge, and here it has minus I effects, Therefore, it can stabilize the negative charge. So they can show both SN1 and SN2 mechanism. Okay, now what is the question? 1 and 3 follows SN1 mechanism. So what is 1? 1 is this one, yes, benzyl halide, and 3 is tertiary halides. Yes, they can show SN1 mechanism. This one is correct. 1 and 2 follows SN2 mechanism. 1 we saw already. 2, what is 2? Okay, so 2 is this one. Yes, this is primary. Okay, this is primary, so this can also show the SN2 mechanism. This is also correct. This looks to me correct. Both are correct. Now the compound 4 undergoes inversion of configuration. Compound 4, this compound 4 undergoes inversion of configuration. Yes, it can go under inversion of configuration through SN2 pathway. As we discussed that, it can show the SN2 pathway, so it can go inversion of configuration. Now, so 1, 3, these are correct. Now D, the order of reactivity for 1, 3 and 4 is more reactive than 1 and 3. So this is saying that 4 is more reactive than 1. 1 is, this is 1, and third is tertiary carbocation. Okay, so we have to understand that is it true or not in with respect to SN1 and SN2 mechanism. Okay, so let's see this order of reactivity with respect to SN1 mechanism. So in SN1, more stable carbocation will react faster. So for sure, we can say that the most stable carbocation will be 4. 4 will give more stable carbocation because it is benzylic carbocation and secondary carbocation at the same time. So this will be more stable. And then, so now we have to see which one is stable, tertiary or this one. So in this case, we have to understand that tertiary carbocation will be more stable as compared to this benzylic, primary benzylic. Secondary benzylic carbocation is more stable than tertiary. So this is more stable, and then will be, so 4 is more stable than tertiary, so it means 3, and then 1. So this will be the order of reactivity towards SN1 pathway. Now let's see what would be for SN2 pathway. So as we said that in SN2 pathway, it is important to stabilize the negative charge. So which one will stabilize the negative charge more effectively? So let's see. So what is happening? Nucleophile is coming. Let's say nucleophile is coming here and the halogen is leaving. Okay, and then you have this is hydrogen and hydrogen. This is the structure of one. In this case, this phenyl group has minus I effect, so therefore it is stabilizing the negative charge of this transition state more effectively. Now when you have structure, this one, fourth, in this case nucleophile, let's draw the same way. So this methyl has plus I effect, therefore it is increasing the electron density of the transition state. At the same time, this phenyl is withdrawing the electron density from this through the minus I effect, and hence we can say that in case of 1, the transition state is more stable than 4th. Therefore this order of reactivity, whether it goes through SN1 or SN2, doesn't follow, and hence the statement 1, 2 and 3 are correct, but 4th is wrong. So this is very important question. So please remember, if you have any doubts, you can write me in the comment box. I will try to clarify it again. So now moving to question number 55. Correct statement about the compounds given below is R. So first, the compound is optically active. So to see the compound is optically active or not, we can do by two ways. One, assign the configuration. You can assign RS configuration and then check, or you can check plane of symmetry. The compound, if has plane of symmetry, then it means it is not optically active. So to see the plane of symmetry, I would suggest first to bring this methyl group in the same plane as this group, giving the rotation around this big carbon-carbon bond. So if you give rotation about 180-degree, then you get this conformation. And if you see that this compound, if you pass the plane, this compound does not have plane of symmetry. Other way is to check by RS nomenclature. So first priority to this chloro, second to this, and third is methyl, fourth is hydrogen. So 1, 2, 3, and hydrogen least priority is far away from us, so this is R configuration, and then this one 1, 2, 3, 4, so this is also R, so it has RR configuration, and hence we can say that it doesn't have plane of symmetry. So therefore this compound is optically active. But if it has, suppose if this carbon has S configuration, then there will be a plane of symmetry, because one chiral carbon has R, another has S, then it is mirror images of each other. Therefore, we can say that it has plane of symmetry. But here, both chirals carbon has configuration R and R. Therefore, it doesn't have plane of symmetry. Now, the second B, they are asking compound possess center of symmetry. If the compound is optically active, then it can't have center of symmetry. So therefore, the compound possess center of symmetry. This statement is wrong. The compound possesses plane of symmetry? No. The compound possesses axis of symmetry? Yes. When the compound is chiral, it has CN axis of symmetry, and you can easily see that this compound, which is conformation of this, if you rotate around C2 axis, which is perpendicular to this line, if you rotate this at this C2 axis, then you get exactly this same molecule, like this molecule. So on rotation, on giving C2 axis rotation, you get indistinguishable isomer, and hence this compound has C2 axis of symmetry. So therefore the correct answer will be A and D. Now moving to 56, which of the following has asymmetric carbon atom? So this is very simple question. You can see that this carbon as hydrogen and hydrogen, this is also hydrogen and hydrogen, so there is no asymmetric carbon. In this case there are two chloro, so this is also not asymmetric carbon. In this case, if you see, one is hydrogen, another is chloro, third is this functional group, and then methyl, so this is asymmetric. Now what is fourth one? In the fourth case, you have methyl OH hydrogen, so this one is asymmetric carbon, but this is not asymmetric carbon. Therefore we can say that compound C and D has asymmetric carbon. So these two compounds C and D has asymmetric carbon. Now moving to the question number 57. Match the following. The Fisher projection of D erythros is shown below. So this is the Fisher projections. And now the question is, D erythros and its isomers are listed as P, Q, R and S in column 1. Choose the correct relationship between PQRS with D erythros from column 2. Okay, so these are the different isomers of the D erythros, and we have to see the relationship between the P and D erythros. So whether P isomer is diastereomer or identical or enantiomer, we have to check. So for this, we should have the knowledge about converting Fisher projection to wedge projection or wedge projection to Fisher projection. So let's see how we can do it. So when you want to convert wedge projection, Fisher projection, so always remember that carbon chain should be eclipsed in the eclipsed position. Okay, so we can say this is something. So this should be eclipsed conformation, and then you have to stand here and see through this. And after seeing, let's say here this is A group, this is B, this is C, this is D. So when you stand here and seeing, then there are two chiral center, so you put like this line, and let's say this is C R C Z. So CR is here and CZ is here. You are seeing from here, so this is your left hand, this is your right hand. Okay, so A group on CR is coming on your left side, so this will be your this will be the left side, and this will be the right side. And group on this CZ carbon, C is on the left side and D is on the right side. So this is the Fisher projection. So now let's convert this wedge projection to the Fisher projection. So first we will rotate around this carbon to bring this aldehyde at eclipsed position. Okay, after rotating this aldehyde 180 degree, then hydroxy goes away and hydrogen comes towards your side, and this remains same as it is, and this is CH2OH. So now we have written this in the eclipsed conformation. So it's easy to draw into the Fisher projection. Just you have to see the molecule from this side. This is your eyes. This is your eyes, and you are watching the molecules through here. Okay, so what is going to happen now? This is CH2OH. You are watching through this, and aldehyde will be on the top. So you are watching through this. This is coming on your left side, hydrogen, and this is on your right side. So this hydrogen is coming on your left side. So left is this one, and OH is on your right side. And now this hydrogen is coming on the left side and his OH is on the right side. So you can see that P is exactly matching to the erythros. So it means P is identical. Okay, now let's see Q. So in case of Q, so you have to do the same. Rotate the Q molecules to bring this in the downside eclipse conformation. This is eclipsed, but it is on the above. So we have to bring these two down. So let's give the rotation around this bone. So when you give the rotation, and aldehyde you are bringing here CH2OH, let's write it, and give the rotation very carefully without. So when you are rotating this, and then hydrogen is going away, OH is coming towards your side, and then in this case when you are giving rotation, then OH is going away and hydrogen is coming to your side. Okay, let's verify again. When you give the rotation around this carbon-carbon bond, then hydrogen is going away and OH is coming to your side, and in this case CH2 case, OH is going away and hydrogen is coming to your side. Now you can draw its Fisher projection easily. Okay, so aldehyde is on the top and you are standing here and you are watching through this. So H is on your left hand, OH is on your right hand, and then OH is on your left hand and hydrogen is on your right hand. So you can see that this molecule and this molecule, the erythros, what is the relationship? So these are not mirror images of each other. So when they are not mirror images, then what are they? Diastereomers. We know that diastereomers are those stereoisomers which are non-mirror images. They don't have mirror image relationship. So therefore, we can say that Q, molecule Q is diastereomers. So P is identical. So P is identical means matching true. Q is diastereomer means 1. So P is 2 and Q is 1. Where is it? Is here. P is 2, Q is 1, and let's see R. What is R? So R, same, give aldehyde, bring aldehyde down, giving by rotating around this bone. So aldehyde is down. This is OH. This is hydrogen. This is OH. And then aldehyde is bringing down, then OH is going away, hydrogen is towards your side. So now what will be the Fisher projection? You are standing here, as I told you, this is your right side, this is your left side, and now you can see that on this group chiral center, OH is on your left side, hydrogen is on your right side. So this is hydrogen is on the left side and OH is on the right side. So now what is the relationship of R? So you can clearly see that R is nothing but diastereomer. So R is also diastereomer. So it is matching to 1. So R is also diastereomer. Now last is S. So if you see the S, so in this case, the Fisher projection, let me erase this molecule. Okay, then S we can quickly draw. Hydrogen is going away, OH is towards your side, and the same hydrogen is going away, OH is on your side. So Fisher projection will be CH2OH watching through this angle. So this is your OH and OH left side, and hydrogen. Okay, so what is the relationship between these and these? So you can see that D erythros and S are enantiomer. So these are the mirror images of each other. These are the mirror images, non-superimposable mirror images. If you see, these are the mirror images. So S is enantiomer. So 3. So the correct answer is C. Now moving to the question number 58, assertion and reason type questions. So 58 question says that vinyl halides do not undergo nucleophilic substitution easily. Yeah, this is correct, because in case of vinyl halide, the halogen lone pair are in conjugation with the pi electron, and therefore it acquires partial double bond character, due to which the breaking of these carbon-halogen bonds becomes difficult. Now we have to see the reason. Even though the intermediate carbocation is stabilized by loosely held pi electrons, the cleavage is difficult because of strong bonding. So what do you think? The reason is correct or not? So let's see what are the options. Both A and R wrong statements. No, because A is correct statement. Both A and R correct statements, and R is the correct explanation of A. Okay, so we have to understand R is correct statement or not. So he's saying that reason intermediate carbocation. So let's make a carbocation first from this vinyl halide. So how carbocations will look like? This will be the carbocation of the vinyl chloride, and it is saying that this pi electron density stabilizing this positive charge. So let's see if you draw this. So we know that pi orbitals. This is the pi bond. I am showing the formation of the pi bond. This is the p orbital, and this carbocation empty p orbital. This is the empty p orbital. This empty p orbital is perpendicular to the pi bond. This empty p orbital of the carbocation is perpendicular to this pi bonded p orbital. Therefore, their pi electron density cannot delocalize in empty p orbital of carbocation. Hence, this reason is incorrect. So the correct answer will be A is the correct statement and R is wrong statement. So correct answer will be D. Moving to question number 59. Molecules. Statement 1 says that molecules that are not superimposable on their mirror images are chiral. Yes, this is correct. Statement 2, all chiral molecules have chiral center. So this is not correct, because we know that allenes molecule, this is the allene. When terminal carbon of the allene have different substituents, let's say this carbon have A substituents and B, this is also have A and B. So substituents on each carbon are different. This compound is chiral, and the chirality is known as axial chirality. So such compounds are chiral due to axial chirality. There is no chiral center. And similarly, biphenyl system, this kind of system, also known for their chirality. If you put very bulky group here, this restrict the rotation around this bond, carbon-carbon bond, the rotation gets restricted, and therefore such molecules also show chirality. So the rotation will restrict, and then this part will be above the plane and this part will be below the plane. So this type of compound called atro isomers. So the statement 2 is incorrect. So the correct answer will be statement 1 is correct, but statement 2 is incorrect. So answer C will be the correct. Question number 60. Cyclobutyl bromide on treatment with magnesium in dry ether forms an organometallic A. The organometallic reacts with ethanol to give an alcohol B. After mild acidification, prolonged treatment of alcohol B with an equivalent amount of HBr gives 1-bromo 1-methyl cyclopentane C. Write the structures of A, B, and explain how C is obtained from B. Okay, so this is the first reaction is formation of Grignard reagent, and we know that Grignard reagents are nucleophile. Therefore, the reaction with ethanol CH3CHO, this is ethanol, so this attacks on the aldehyde, and reaction with the aldehyde gives secondary alcohol after acidification. So they are saying mild acidification, so after acidification you will have secondary alcohol. After having the secondary alcohol, the reaction is with HBr, and we know that HBr will provide acidic condition, or dilute H2SO4 gives dehydration. So this is dehydration reaction. So what is going to happen? First, protonation will take place. After protonation, this positive charge comes here, so it pushes the water to go away and gives carbocation. This carbocation wants to stabilize, and we know that 4-membered ring are unstable due to two reasons. One is angle strain, second is torsional strain. Therefore, it wants to stabilize to expand the ring. So ring expansion will take place through 1,2-alkyl shift to give the 5-membered ring. So now you can see this is going here, will come this place. So this is 5-membered, and now this carbocation again want to stabilize through 1,2-hydride shift to give more stable tertiary carbocation. This is the tertiary carbocation, and now this tertiary carbocation will further attack by the bromide ion, because in the reaction mixture there is a bromide from this one. Therefore, it will give you the desired product C, 1-bromo 1-methyl cyclopentane. So A is this Grignard reagent, B is this alcohol, and C is this one, and they are saying explain the formation of C. Since 4-membered ring are unstable due to angle strain and torsional strain, so it undergoes ring expansion to stabilize this carbocation, and further rearrangement take place. And we know the stability orders 4-membered is less stable than 5-membered, and 5-membered is less stable than 6-membered. So this is the stability order. I hope this question is clear to you. Now next question is identify the pairs of enantiomers and diastereomers from the following compounds. So if you see, these are stereoisomers, and the best way to draw the mirror and check this OH is here, yes, hydrogen is here, yes, OH, no, this is OH here. So 1 and 2, we can easily find that 1 and 2 are diastereomer, because diastereomers are non-mirror images. So diastereomers doesn't have mirror image relationship. Now 1 and 3, let's see, OH, yes, hydrogen, yes, hydrogen, yes, OH, yes. So 1 and 3 are enantiomer, because enantiomers are mirror images, non-superimposable mirror images. Okay, now moving to question number 62. The first reaction is the reaction of primary bromide with ethanol at high temperature. So here This is the primary, so it undergoes substitution through nucleophilic to give this as a major product. Second reaction is the reaction of with alcoholic KOH heating. So alcoholic KOH provides ethoxide as a base, which is a strong base, so elimination is going to take place. This is the example of elimination reaction. So what you will get this beta hydrogen will abstract by the base to give CH double bond CH phenyl. Now the substituents at this carbon is hydrogen and phenyl, which are different, and same is here, so it can show cis and trans geometrical isomers, and trans will be major. Now moving to question number 3rd. The first reaction is with alcoholic KOH and then HBr. So we can say that first reaction is giving the alkene. So let's draw alkene directly. So abstraction of this proton will give you this, and this is Saytzeff product. According to the Saytzeff rule, we already learned that in some cases you can see the Hofmann product. For Hofmann rule, it is important to have beta hydrogen acidic, and this acidic can be due to fluoro or alkyl ammonium ion. When you see such kind of group present, then it makes the beta hydrogen acidic, and in that case less substituted alkene major product, and in case of Saytzeff, more substituted alkene is major product. Okay, now this reacts with HBr, second step reaction with HBr, and HBr reactions will follow Markovnikov's rule because there is no peroxide. According to Markovnikov's rule, hydrogen goes to the double bonded carbon which having more number of hydrogen atoms, and Br goes to another double bonded carbon. But here both double bonded carbon have only one hydrogen, same. So here we should understand that the principle of Markovnikov's rule. So Markovnikov's rule says that hydrogen ion goes to the double bonded carbon having more hydrogen because it gives more stable carbocation. So here we have to see which gives the more stable carbocation, and therefore we can say that the proton should go this carbon, not this one. So it will give you benzylic carbocation after adding proton here, and benzylic carbocation are more stable due to resonance stabilization by the phenyl ring, and after that bromide will attack to give you the desired product. You know what will be the product. Okay, now moving to the next question. Boil alkali. So this is alkyl chloride, you can see that, and under harsh condition this will undergo substitution of both chloro because it is very harsh condition boiling with alkali, and now this hydroxy group on one carbon is unstable, so it will give you, after removal of water molecules, CH2CHO, aldehyde will come. Now question number 5th. Here is very simple because you have only one beta hydrogen, there is no other beta hydrogen, therefore the product will be this chloro will go, so double bond CH3, and here methyl. Now bromoethane reacts with 1/2 of molar quantity of silver carbonate. In this case bromoethane C2H5Br reacting with silver carbonate. So this is the structure of carbonate. So each oxygen will take ethyl group. So what will be the product? This will be the product. Now chloroform reacts with the aniline in presence of alkali. So this is the carbylamine reaction. And we know that in this reaction isocyanate will form. NH2 with KOH plus CHCl3 will give you bad smelling compound, which is isocyanate. Now moving to the next Question number 63 is very interesting. An alkyl halide X of formula base C6H13 chloro on treatment with potassium tertiary butoxide give two isomeric alkenes. It means there is a elimination, and this alkene on hydrogenation reactions, we know that it saturates the double bond, so it will give 2,3-dimethyl-butane. So we know only the structure of 2,3-dimethyl-butane. So let's draw the structure of 2,3-dimethyl-butane. Okay, this is the 2,3-dimethyl-butane, and this is forming by the hydrogenation of Y and Z. Both are giving the same product. So we can say that there is a two possibility that double bond can be at terminal position and in the middle. So either of these could be Y or Z, because now you can see that if hydrogen add to this, you will get the same product. Now we have to understand what could be the structure of X. So you have to put the chloro in between on the second carbon. So let's put chloro here. Even you can put chloro here, it is the same structure. Okay, now you can clearly see that after elimination reaction, if you remove this beta hydrogen, then you get this compound, and if you remove this beta hydrogen, then you get this compound. So this is the structure of X, and Y could be any one of them. So Y and Z could be any one of them, but X, this is the structure of X. So we can say that X is this one, Y this one, or you can say Y this one, doesn't matter, and Z this one. Now moving to the 64, draw the stereochemical structure of the products. So this is the SN2 reaction, and we know that in SN2 nucleophile attacks from the back side, and then this leads to the inversion of configuration. So what will be the product, because we have to write in the Fisher projection form. So hydrogen will come here, nucleophile will be here, and this. So this will be inversion of product. Now arrange the following in increasing order of nucleophilic substitution reactions. We know that nucleophilic substitution reactions favors if the leaving group is stable, and the stability order is iodide is more stable than bromide, and bromide is more stable than chloride, and fluoride is more stable. Therefore, the order of reactivity will be CH3I will react faster than CH3 bromide. So there is no exception. Question number 66. An organic compound X on analysis gives 24.24 percentage of carbon and 4.04 percentage of hydrogen. Further, sodium extracts of 1 gram of X gives 2.9 gram of silver chloride, and further acidified with silver nitrate solution. Then silver nitrate solution, the compound X may be represented by two isomeric structures Y and Z. So compound X can be represented by two isomeric structure Y and Z. Y on treatment with aqueous potassium hydroxide. When you treat Y with potassium hydroxide, then you get dihydroxy compounds. So dihydroxy compound means something like this dihydroxy compound, and Z on treatment with gives ethanol. So Z is giving CH3CHO. Okay, find out the molecular formula of X and give the structure of Y and Z. Okay, so first we have to understand that silver nitrate solution is reacting with X, so it means X has alkyl halide, or we can say alkyl chloride, because that's why this silver salt precipitate is forming, and then you get the carbocation, and this silver salt precipitate amount is 2.90 gram, and the molecular weight of silver chloride is we should know the molecular weight of the silver chloride is 143.5 gram per mole. So we have to calculate the percentage of chloride in silver chloride, and it will give percentage of chloride in X compound. So 35.5 is the molecular weight of chloride, multiply by 2.9 gram, divided by the molecular weight, then multiply by 100. So after solving this, it will come around percent. So this is the percentage of chloro, and we know the percentage of carbon percentage is 24.24, hydrogen percentage is 4.04, and now chloro is 71.72%. So divide them by their molecular weight, then you will get the relative number. So dividing by molecular weight, so it will divide by 12, so it will be 2 divided by 1, 4 divided by 35, so it will be around 2. Then the simplest ratio will be 1, 2 and 1. So the empirical formula will be 1 carbon, 2 hydrogen, 1 chlorine. So this will be the empirical formula CH. Okay, so we determine the empirical formula of X. This is the empirical formula of X. Now it is saying that X has two isomeric structures, and treatment one gives this, another is giving this. It means the formation of this compound indicates that chloro are present on different carbon atom like this, and in this case it is indicating that halogens are present on the same carbon. This is CH, CH2, CH2, this is CH, and this one. Therefore we can clearly say that the structure of Y this, and this is the structure of Z, and hence molecular formula of X will be C2H4Cl2. This is the molecular formula of X, a structure of Y, and this is the structure of Z. Now question number 67. What effect should the following resonance of vinyl chloride have on its dipole moment? So this is the vinyl chloride structure, and this is its resonating structure. So before answering this question, I would like to tell you some general rules about the resonance effects on the dipole moment. So if the resonance creates charge separation opposite to the inductive dipole, then dipole moment decreases. So the resulting dipole moment decreases when the resonance creates charge separation, which is opposite to the inductive dipole. For example, in case of chlorobenzene, the dipole moment direction is from carbon to chloro side, because chloro is more electronegative. So the dipole moment direction is here, you can see. But during the resonance, the positive charge comes on the chloro and negative charge on the carbon, and therefore the direction of the dipole moment is reversed, and hence the resulting dipole moment will be less than expected due to this resonance, and same for aniline also. Okay, now the another condition in which resonance reinforces the inductive dipole moment and increases the net dipole moment. For example, in nitrobenzene, the direction of dipole moment is from carbon to nitro, and in the resonance also you can see that the direction is the same, so the net dipole moment will be more than expected in this nitrobenzene case. Okay, now moving back to the problem. So here you can see that the direction of the dipole moment was this one, from carbon to chloro, but in the resonating structure the dipole moment direction is reversed, and hence the net dipole moment will be less than the expected. Therefore the resonance of vinyl chloride decreases the dipole moment. Okay, now moving to next question, 68. Write the structure of all possible isomers of dichloroethene. Which of them will have zero dipole moment? So dichloroethene, so two carbon are there, 1 and 2, double bond is there, and 2 chloro is there, and this is the hydrogen. So this is one structure, and another structure could be in this chloro you can put on different carbon with this trans geometry. This is the trans. So the dipole moment of this bond and this bond are opposite, cancelling each other, And similarly here, the dipole moment of carbon hydrogen, this carbon hydrogen are in opposite direction, so it cancels each other, so therefore this will have zero dipole moment. So dipole moment will be zero for the transsymmetry. And now the third structure will be cis chloro here. So this is the third structure. 69. State the condition under which the following preparations are carried out. Give the necessary equation. Need not to be balanced. Okay. Lead tetraethyl from sodium lead alloy. So sodium lead alloy, we have to make C2H5 this one. So for this we can do the reaction with alkyl halide. Therefore the another product will be sodium bromide and lead. So we don't need to balance. So if you want to balance, then you can put here 4. This will be 4 and this will be lead will be 3. Okay, now methyl chloride from aluminium carbide. So this is the structure of aluminium carbide. So aluminium carbide on hydrolysis gives methane gas, and then you can do chlorination in the presence of light to get the methyl chloride. Now moving to question number 70. Show by chemical equation only how you would prepare the following from the indicated starting materials. Specify the reagents in each step for the synthesis. Hexachloroethane from calcium carbide. So calcium carbide, we have to get CCl3, CCl3. So calcium carbide on hydrolysis gives calcium hydroxide plus C2H2. This is alkyne. This alkyne can be reduced by hydrogenation to give C2H6. And now we know that we have to get 6-chloro. So we have to do over chlorination. Therefore we can use chlorine with light and in excess. Then we will have C2Cl6. Next is chloroform from carbon disulfide. So this is the carbon disulfide and we have to make chloroform. So for this we can do first the reaction with the chlorine, and then it will give you carbon tetrachloride plus S2Cl2, and after that you can reduce this carbon tetrachloride with hydrogen in the presence of iron to give chloroform. Now next is give one chemical test which will distinguish between ethanol and chloroform. Okay, so we don't know which one is ethanol and which one is chloroform. So if you remember that chloroform is used in carbylamine reaction. Yeah. So let's take, don't know which one is chloroform. So let's say if you take compound A and reacting with KOH plus aniline, if you get the bad smelling compound, then you can clearly say that it is chloroform. But if you don't see any bad smell, then it will be ethanol, because the bad smell comes from the formation of isocyanide, when you have chloroform in the reaction mixture. But ethanol will not give this test. Topic 2, preparation and properties of haloarenes. And the question number 1, the decreasing order of reactivity of the following compounds towards nucleophilic substitution reaction. This question is very important. Therefore, I would like to explain you in detail, and I will take your time a bit more. So first we should know the order of reactivity in SN2 reaction depends on its stability of transition state. If the transition state is more stable, then reaction will be faster. And which transition state will be stable? So if the reactant have minus I or minus M or both, then it can stabilize the negative charge of transition state. So for example, when we have nucleophilic substitution reaction, then let's imagine this is the reaction, and in this case nucleophile is attacking and halogen is leaving. If this R group has minus I minus M, then it can stabilize the negative charge through its inductive effects. So this is very important to understand that transition state carries negative charge. So therefore negative charge should be stabilized. So if the reactant has minus I or minus M effect, then it can stabilize the transition state. Therefore we have to see out of these four options which one has very strong minus I and minus M effect. In this case, first case, this is there is no substituents, nitro substituents. In the second case, nitro is at ortho position, and we know that nitro has minus I and minus M effect when it is present at ortho position. At meta, it has only I effect, and I effects decreases with distance. So I effects at ortho position will be more than at meta position. Now look at here. In case of 3, here is only minus I effect, and this one has minus I and minus M. Resonance effect is same at ortho or para position. Resonance effect doesn't change with the distance, but minus I effect is more at ortho and less at meta and more or lesser at para position. If this is clear to you, then you can clearly say that the stabilization of the negative charge in the transition state will be more for 2, because in fourth case you have only minus I effect, no resonance, minus resonance effect is not there. So which one will be more reactive? 2 will be more reactive, and then third, because third has minus mesomeric effect as well as inductive effect, so third will be the less reactive as compared to 2, and then 4, and in the last one. So which one is matching? B is matching. Again I would like to explain you, in the SN2 reaction, transition state carries negative charge, so stabilization of negative charge is very important for higher reactivity. And among these four options, 2 is stabilizing the negative charge more effectively, because in 2 minus I effects and minus M effects both are there, but minus I is more as compared to option 3, because in option 3 nitro is at para and therefore inductive effect is less as compared to at ortho position, but meta doesn't have any resonance effects, and same is here. And now as I told you, resonance effect is same whether it is at ortho or para position, but inductive effects decreases with the distance, or here inductive effect is more and here it is less, and in this case you have only inductive effects, no mesomeric effects. Therefore this is the correct answer. This is very important question. If you understand this, then any questions coming from this topic you can easily answer them. Moving to the question number 2, the major product of the following reaction. So the given reaction having sodium borohydride, which is a reducing agent, and it can transfer the hydride. So we have to understand that there are 3 reducing group: ketone, double bond, and imine. And we should know the properties, chemical reactivities of the sodium borohydride. Sodium borohydride reduce aldehyde to primary alcohol, ketone to secondary alcohol, and it can also reduce imine to amines. Which functional groups sodium borohydride cannot reduce are ester, carboxylic acid, cyanide, nitro, halogen. These functional groups cannot be reduced by sodium borohydride, but it can be reduced by lithium aluminum hydride. Even lithium aluminum hydride can reduce all these functional group also because it is very strong reducing agent. Now let's see in the question. So as we said, it can reduce ketone. Yes. Can it reduce the double bond? No. It cannot reduce the double bond because this double bond is not in conjugation with this ketone. If it was like this, then it can reduce to give 1,4 reduction product. This is 1,4 reduction product. This is also depending on the cases. Not every time you will get the 1,4 reduction products. Okay, so this double bond will not reduce. Okay, this imine will reduce. Yes, so this is not the correct answer. This is also not the correct answer. Here, as we said that double bond can't reduce because it is not in conjugation with this ketone. So this is also not correct answer. The correct answer is this one. Okay, so let's talk about a little bit more about the situation in which double bond in the conjugation. For example, if you have this substrate and you are doing reaction with sodium borohydride, then you get 50-50% of 1,2 reduced product. This is 1,2 reduction product plus 1,4 reduction product. Almost 50-50% you get these two products. Since this double bond is not in conjugation, so it will not reduce. So correct answer is D. Now moving to the question number 3. The major product obtained in the following reactions. So the given reaction, if you see, is secondary benzylic halide. And in this reaction, tertiary butoxide is given. So tertiary butoxide is a bulky base. This is not a nucleophile. This is a base, bulky base, and heating at a high temperature. So it means nucleophilic substitution is not possible. Therefore, you can remove this option A, which is forming by the nucleophilic substitution if the reaction follow the SN1 pathway. But as we said, this is not a nucleophile. So option A we can easily rule out. Now option B is forming by the elimination reaction. We will come on this option later on. Let's check option C. So option C is plus, and this is also the nucleophilic substitution. So plus minus, we cannot predict whether it will be dextrorotatory or levorotatory. So just by thinking this way, we can easily rule out option C and D. So what is left? Option B. So let's explain how B is forming. So since the base is bulky and it is very strong base as well, and it is under high temperature, so what is possible? The reaction is following either E1 or E2 mechanism. Since we have a strong base, so therefore we can rule out E1 pathway. So the reaction is following E2 pathway, and you can understand what is happening in E2 pathway. The base abstracting the proton, and at the same time halogen is leaving out and giving the alkene, and the trans will be the major product. So correct answer is B. Okay, now moving to question number 4. In nucleophilic substitution reaction, alkyl bromide reacting with the chloride in DMF and it giving alkyl chloride. So this reaction indicates that this is the substitution reaction in which chloride is replacing the bromide, and it is and it is SN2 reaction because inversion of configuration is taking place. So now the question, which of one of the following undergoes complete inversion of configuration? So for complete inversion of configuration, first of all, the compound must have chiral center. So let's see, in option A, if you draw, so carbon have hydrogen, bromo, and then 2-phenyl group. So it does not have chiral center. So we can't talk about inversion of configuration in this case. So ruled out this option. Next one is 2 hydrogens are there. This is also not chiral center. So ruled out this option. Now option C. In option C, carbon is attached to hydrogen, methyl, bromo, and phenyl. Yes, here we can talk about the inversion of configuration. Let's check option D. In this case, we have carbon have 1 phenyl and methyl. After that, this bromo, and then again phenyl. So again this is not possible because it has 2 same group. So this is not chiral. So only chiral compound is C. So therefore inversion is possible only in C. So the correct answer is C. Now moving to the question number 5. This question is very interesting. Compound A, this is the compound A formula, gives a yellow precipitate when warmed with alcoholic AgNO3 silver nitrate solution. Oxidation of A gives an acid. So oxidation of A, after oxidation it is giving B, which is an acid, and then this easily forming the anhydride on heating. Identify the compound A. So let's look at the first option. So after seeing this option, we can easily say that this compound has 1 benzene ring. Okay, now how many carbons? 6 carbons are there. So we don't know what are the 2 carbons and where is the position of the halogen. So these are the missing information. Okay, so what is given next? Oxidation of A. So A on oxidation gives, what is giving? Carboxylic acid. So for sure this indicates that the benzene ring has methyl group, right? But we don't know how it is aligned. But we should remember that benzene ring having benzyl carbon and at least 1 hydrogen and anything else, 1 hydrogen and anything else attached on oxidation with the KMnO4 gives carboxylic acid. This we know clearly. So therefore if you have methyl or ethyl, it can give you oxidation to carboxylic acid. This we clearly understand. What else is given? So next information is given that it can form anhydride. So remember that acid forms anhydride only when they are in a close proximity. When they are in a close proximity, and it can form 5-member or 6-member, then only it can form the anhydride. So let's say when they are in a close proximity, they can give you anhydride like 5-member, and 5-member anhydride are stable. Okay, so now next important thing
it gives yellow precipitate when bound with alcoholic HNO3. Here I would like to inform you that alkyl halide, let's say this is alkyl halide, when treated with silver nitrate solution, it could be aqueous, alcoholic, doesn't matter. So in this given case, it is alcoholic HNO3. So HNO3 is not a nucleophile. Okay, so what is happening? First, it will form the coordinate bond with the silver ions. So it can form the coordinate bond with the silver ions, and after that, nucleophile attack. So what is nucleophile here? Is alcoholic. So what is the formula of alcohol? This is the formula. So this is attacking as a nucleophile and giving you OR plus silver bromide as a precipitate. So we understand that alkyl halide reacts with the silver nitrate, gives silver bromide as a precipitate. What do you think about this case? Do you think it is possible in this case? So in this case, it is not possible. It can form the coordination bond. It can form the coordination bond with this bromo like this, but nucleophile attack at this position and breaking this bond is difficult. Formation of this is difficult because we know that carbon halogen has partial double bond character. We know that it has partial double bond character, therefore it is difficult to break. It means if halogen is directly attached to the benzene ring, it is difficult to break. So therefore in this case, option B, you can see that it is directly attached to the benzene ring. So this is not possible. First reaction is not possible with this. Okay, so what about option A? Yes, first reaction is possible with this benzyl halide, because this is primary carbon and it has only single bond character, so it is possible to break. Okay, but oxidation of A gives acid. Yes, this is possible. It can give the carboxylic acids, but after that, can it forms the anhydride? Option A, you can get this kind of carboxylic acid, but it cannot form anhydride, because anhydride it should be like this, and this is very big cycle and they are not in a close proximity, so this cannot form anhydride. Okay, let's look option C. So option C is also the same, like this part oxidize to give carboxylic acid, and this part is also giving carboxylic acid, but it cannot give anhydride. It can combine with the another molecule of the benzene ring to form the anhydride, but then formula will not be like this, right? So this is also not possible. So what is possible? Option D. In option D, this is possible that it forms the anhydride easily, because first you will get this kind of carboxylic acid, and then on heating you get this 5-member stable anhydride ring. Okay, one more time, I would like to tell you that anything on a benzylic carbon having at least one hydrogen can easily undergo oxidation to carboxylic acid. This is clear to us. So therefore, we can easily understand that this CH2Br can oxidize to carboxylic acid. And then methyl, we know that methyl oxidation gives carboxylic acid. But we have to choose the orientation of these two groups, and the best orientation will be D, because then only you can get anhydride on heating. So I hope it is clear to you now. Now question number 6. The Wurtz-Fittig reaction involves condensation of. So we know that in Wurtz involve the condensation of 2 alkyl halide, and in the Fittig reactions involves 2 aryl halides. But in Wurtz-Fittig reaction, it involves the condensation of alkyl halides and aryl halides. So, which is the correct answer? 2 molecules of aryl halides? No. 1 molecules of each aryl halides and alkyl halides? Yes. 1 molecule of each aryl halides and phenol? No. 2 molecules of aryl halides? No. So the correct answer is B. Now moving to the question number 7. Aryl fluorides may be prepared from arene diazonium chloride using, first option is the correct answer, tetrafluoroborate on heating with diazonium salt gives fluorobenzene, and this reaction is known as Balch-Siemens reaction, and the rest options are incorrect. Okay, now moving to the next one. The major product of the following reaction. So this is the benzyl halide, and we know that benzyl halide can show SN1 and SN2 reaction because it stabilizes the carbocation as well as transition state of SN2 reaction because of the phenyl having -I effects and -M as well. So we know that it can show SN1 or SN2 reaction, and we know that this is very strong nucleophile because sulfur has, whenever you see the negative charge on sulfur, it has high tendency to give electron density because of low electronegativity. And DMF, it means it is a polar aprotic solvent, and we know that polar aprotic solvent is used in case of SN2 reaction. Okay, so what are possibility here? So let's say if this phenyl sulfide attack, then this product is possible through SN2 pathway. This product is possible if the reaction is taking place from the same side. So we know that in SN1 you get retention. This is the retention product as well as inversion. So only you are seeing only retention here, no inversion product. So this is also not possible. What about option C? In option C, they are replacing the fluoro. Do you think it is just it is impossible to replace fluoro? There is no logic behind it. Actually, there is a logic behind it. You can replace the fluoro, and this reaction is known as nucleophilic aromatic substitution reaction. So this is very well known reaction. Don't think that like that this is they just replace the fluoro without any logic. No, this is called nucleophilic aromatic substitution reaction. But in this case, is it possible to replace the fluoro? So let's understand. Actually, fluoro could be replaced if nitro was at para position, and in this case, if nucleophile attacks, then negative charge comes in the ring, and this negative charge can be stabilized by the nitro group through the resonance. So it goes here and then follow up. So in this way you can draw further resonance. You know what is those are the resonating structures. So, and after that this fluoro goes away and nucleophile comes. So this is possible if nitro was at para position, but in this case it is at meta position, so it is not stabilizing the negative charge. Therefore, substitution only at this position is not possible. Okay, now but it could be minor product. There is a possibility that it could be minor product. Okay, we can't rule out this one. What about option D? In option D, they are replacing both this one and this one. Okay, this is also possible, but what they did, they are showing retention of the configuration. Okay, and fluoro replacement also. So this cannot be the major product. This cannot be the major product. So what will be the major product? Major product will be A, because the reaction will follow the SN2 pathway, and due to the strong nucleophile and polar aprotic solvent, and at the same time benzylic halide stabilize the transition state due to its -I and -M effect. Therefore, we can say that the correct answer is A, not B, C or D. If you have any doubt regarding question number 8, please ask me in the comment box. Now moving to the question number 9. When phenyl magnesium bromide reacts with tertiary butanol, the product would be. So magnesium bromide, we should know that whenever you react the Grignard reagent with any acidic medium which can provide the proton, which can provide the hydrogen, so what is going to form? Hydrocarbons will form. So what will be hydrocarbons here? This, and this is nothing but benzene. So the correct answer will be A, benzene. Now moving to the question number 10. How many structures for F are possible? So in the given reaction, this secondary alcohol in the presence of acid losing the water molecule giving the F. So F for sure it is alkene, and then after bromination getting 5 products. Okay, so let's understand this reaction through mechanism. This is the secondary alcohol reacting with the acid. So first step is the protonation of the OH, we know that, and followed by the removal of the water molecules to give the carbocation. This is secondary carbocation. There is no possibility of rearrangement, so what is going to happen? Removal of the hydrogen. So this is, let's say, HA, this is, let's say, HB. So when HA will goes, then you get this double bond in the middle. If you remove the HB, then you get the double bond at the terminal position. So there is also possibility that you can get the cis geometry. So one is this, second is this, third is this. So how many structures of F are possible? 3. So let's go back to the problem and check which is the correct option. 2 no, 5 no, 3 is the correct option. For our understanding, we should also understand how these many products are forming. So they are showing 5 products. So let's try to understand. So if you do the bromination of these, we know that bromination is the anti-addition, and it leads to the bromination at both the double bonded carbon atom. Now if you see here, there is a 1 chiral center. So therefore there is a possibility of D and L enantiomer. So we get 2 products from here. Okay, now coming to the interesting part. So you have transalkene plus bromination. So what will you get? We know that you will get either meso or racemic mixture. But the trick to remember that, I told you in my last video how to remember this, and I always use a mathematical analogy. So what is this mathematical analogy? I want to tell you again. We know that this is anti-addition reaction, and we can call anti, let's call it trans addition reaction. So I use my mathematical analogy, trans geometry minus trans addition gives 0. So 0 means meso compound, because meso compound has optical rotation 0. So it means I can understand there, therefore this will be meso compound and it will be only 1. Okay, now if you have cis geometry and it is bromination, which is anti. So cis geometry minus trans addition, you will get non-zero. So in this case you will have racemic mixture. So how much compound you will get? 2. Racemic mixture means enantiomers. You will get in this case also enantiomers. So 2 from this 2 1 2, so total 5. 2 plus 1 plus 2 is equal to 5. So you will get total 5 products in this way. If you have cis geometry and let's say you have osmium tetraoxide and we know that this is cis addition reaction. So in this cis addition reaction you will have dihydroxylation, and this dihydroxylation cis minus cis is equal to 0, so it will be meso compound. So this way I easily remember whether it will be meso or racemic mixture. I hope this is clear to you. Now let's move forward. Moving to the question number 11. The reaction of toluene with chlorine in the presence of ferric chloride gives predominantly. So this reaction is the example of electrophilic substitution reaction. So this is the structure of toluene, and when you react with the chlorine in the presence of FeCl3, then it generates the Cl positive as electrophile, and this electrophile attached to the benzene ring. And now we know that methyl has plus I effects, therefore it is ortho and para directing, and hence there will be a mixture of product chlorine at the ortho plus we know that para will be major product. Okay, so what are the options? Benzoyl chloride? No. Metachlorotoluene? No. Benzyl chloride? No. Ortho and para chlorotoluene. So the correct answer is D. If they were asking only one of the major product out of ortho and para, then para will be the major product. Now moving to the question number 12. Chlorobenzene can be prepared by reacting aniline with hydrochloric acid? No, because aniline on reacting with HCl just will give salt, nothing else. Cuprous chloride? No. Chlorine in presence of anhydrous aluminum chloride? No, this will lead to the chlorination of the benzene ring. Nitrous acid followed by heating with cuprous chloride? Yes, this is the correct answer, because when you react with the aniline with nitrous acid at 0 degrees Celsius, then you get the diazonium salt, and this diazonium salt can be decomposed by cuprous chloride to corresponding Cl. If you use cuprous bromide, then it gives bromobenzene. This is the example of Sand-May reaction. Okay, now true or false. So in question number 13, metachlorobenzene is an isomer of metabromochlorobenzene. So let's draw this structure first. So this is put chloro and this is the bromo, and in this second case if you put first bromo and then chloro, so if you see these molecules are identical, so they are not isomer, and hence it is false statement. Okay, now moving to question number 14. Choose the correct option for the following set of reactions. So this is the reaction of this molecule with the Grignard reagent followed by hydrolysis gives Q, then treating with concentrated HCl. Okay, after looking the option, we can easily understand that this compound has cyclohexane ring, and this cyclohexane ring having oxygen, So after this, putting this oxygen like a ketone, then it satisfies this formula: 1 2 3 4 5 6 carbon, 10 hydrogens, 2 2 2 2 2, 10 hydrogens. So this is the formula of this. Now it is reacting with the Grignard reagent. So when it reacts with the Grignard, we know that Grignard is a nucleophile, and this alkyl will go here and then followed by hydrolysis to give tertiary alcohol, and this is the structure of Q. And after that they are asking reaction with concentrated HCl. So in this case, concentrated HCl, what it will do, it will remove the water to give the carbocation like this, and this carbocation will get further attacked by the chloride because it is concentrated, so chloride concentration is very high, so it will attack here and give CH3Cl, and this is the structure of S. So if you see, S is this, yes, correct. And okay, so we have to actually draw all the structures because they are asking every structure T, R, U, and this is MCQ with one or more than one correct answer. So there could be more than one correct answer. So let's draw other structures. And there is a reaction of Q. This is the reaction of Q. Actually its arrow is here, with phosphoric orthophosphoric acid, and this is 20%. So it is providing the dilute condition, and in dilute condition Q is the OH, has OH group. So what is going to happen in this case, after removal of water, this gives the carbocation, and this carbocation will not get attacked by any nucleophile because PO4 is not a nucleophile. So what is going to happen? Elimination. So hydrogen from the beta position will go away and it will give more substituted alkene according to the Saytzeff rule. Therefore the correct structure of R will be this, and then R is treated with the Rani nickel. So after treating with the Rani nickel, this double bond will get saturated and you will get hydrocarbon, and followed by bromination in the presence of sunlight. So this bromination will be radical mechanism. It will give bromo radical, and this bromo radical will go to the more stable radical, and tertiary radical is the more stable one. Therefore the reaction will take place at this carbon. So this will be the structure of T. And now R on reacting with HBr in the presence of peroxide, so it will follow the anti-Markovnikov's rule, and according to this rule hydrogen will go to the double bonded carbon which have less number of hydrogens, so it will come here, and bromo will be here. So this will be the structure of U. So let's check how many correct answers are there. So S is this, yes. U, what is the U? Yes, U, structure of U. So A is the correct answer. So B, in case of B, U is this, yes, this one is correct. And what about T? Let's check the T. What was the T? T is this one, yes, T is also correct. So A and B are correct. Let's see the C. U is this, no, this is not the correct one. S, what was the S? S was directly attached to the chloro, so this is also not correct. And D, in case of D, S was, yeah, this is not the correct structure of the S. Okay, so only two options are correct, A and B. This is the correct answer of this question. Now question number 15. Benzyl chloride can be prepared by toluene, chlorination of the toluene. So to prepare this one, This is possible only when you do the radical reaction, and for the radical reaction you need chlorine in the presence of light. So therefore only this is the source of the Cl radical, and rest of the reagents you can easily rule out. So the correct answer is C. 16. Aryl halides are less reactive towards nucleophilic substitution reactions as compared to alkyl halides due to. Okay, so we know that aryl halides are less reactive towards nucleophilic substitution reactions because of the partial double bond character of this carbon halogen bond due to the resonance. So the formation of less stable carbonium ion, this is not valid, because if this bond will not break, then it cannot form the uh, carbocation. So there is no sense to talk about the stability of carbocation. Resonance stabilization, yes, as we have seen. Longer carbon halogen bond, this is not correct, because this carbon is sp2 hybridized, and due to which the carbon halogen bond is shorter, not longer. The inductive effect, this is also not valid. sp2 hybridized carbon attached to the halogen, yeah, this is the correct. So B and E are the correct answer for this question. Moving to the question number 17, match the following. So in column 1 we have to match with the column 2, and they are saying that it can match with more than one item. So let's check it. So okay, this is the halide on reaction with, okay, this is all together, actually this is all together, and this one is together with this like this. Okay, so what they are asking, this halides on reaction with ethoxide gives alkene. So this is E1 reaction, E2 reaction, even C1 reaction or first order reaction. So first we should understand that whenever you see primary halides, so there is a possibility of E2, not E1, and for E2 we need strong base. For E1 we need weak base is enough, and it's shown by secondary or tertiary halides. But in the given question we have only primary. So look at this, A is primary halides as we said, therefore it will match to E2 reaction. So A will match to Q, E2 reaction. Only one option, it is matching to one option. Now let's look at the B. B is secondary halides, both are secondary halides. This is deuterium, instead of hydrogen this has deuterium, this has hydrogen. So secondary halides will give E1 mechanism, therefore we can say that B is matching to P, E1 reaction, and we know that E1 is first order reaction, therefore it will match to the S also. So first order reaction. Now look at the C. So this is primary halide on treatment with ethoxide gives ethoxides, and this deuterium labeled ethanol gives alkene, and in this alkene you can see that deuterium is coming on this carbon. What does it mean? So how it is possible? So let's look at this. You have CH2 Br, and after this you are getting alkene, and in this alkene the deuterium is coming at beta position, alpha position, beta position with the double bond. So this is possible only when the reaction is following E1 CB mechanism, because in this reaction the mechanism will be, first it will be the abstraction of proton by base to give the carbon ion, which is a conjugate base, and therefore that's why the reaction name is conjugate base. So it will form carbon ion like this, and this carbon ion can take deuterium from ethanol, this deuterium ethanol, to give you something like a deuterium level species like this. And after that another proton can be taken away and to give this carbon ion, and then followed by removal of this halogen to give you this deuterium labeled product. So hence this reaction is following the E1CB reaction, and this is also first order reaction. So C is also matching to R, E1CB and S first order. So it is also matching to 2. This is also. Now let's look at the D. This species reacts faster than this one on reaction with ethoxide in ethanol. Okay, so this is the primary halides and reacting with faster than this. So this is also the example of E2 reaction, because this is, first of all, this is primary halides. Second reason, this is ethoxide is a strong base, therefore it will lead to the removal of the proton, beta hydrogen you can say, and halides at the same time. Therefore D is also following the E2 mechanism. So this is the correct matching. Now moving to the question number 18, assertion and reason type question. So what they are saying, statement 1, bromobenzene upon reaction with bromide. Statement 1, bromobenzene upon reaction with bromine in the presence of iron gives 1,4-dibromobenzene as the major product. So this is the example of electrophilic substitution reaction, and para is the major product because bromo halogens are orthopara directing group. So this is the major product. So first statement is correct. Now statement 2, in bromobenzene the inductive effect of the bromo is more dominant, yes this is true, than the mesomeric effect in the directing the incoming electrophile. Inductive effect of halogens are dominating over plus M effect. This is true statement, but this is not the reason to direct the incoming electrophile. Hence statement 2 is incorrect in context of directing the group. In context of directing the group, it is incorrect. So the correct option is statement 1 is true, statement 2 is false. So C is the correct answer. Again I would like to repeat, statement 2 up to the half is correct, that bromo group is more dominant. Inductive effect minus I effect of halogens are dominating over plus M. This is true statement, but this is not true in the context of directing the incoming electrophile. So which effects directing the electrophile? The positive mesomeric effect of bromo direct the electrophile at ortho and para position. This is the correct reason. Hence we can say that statement 2 is incorrect. Now moving to the question number 19 subjective problems. Give reasons for the followings. So on reaction with aqueous ethanol, this is the tertiary halides, and tertiary halides can decompose to give easily tertiary carbocation, and you will have bromide in the reaction medium. This bromide will take the proton from the ethanol to give the HBr, and this HBr will create acidic solution. But in case of this case, this carbon halogen bond has partial double bond character because it is directly attached to the ring. Therefore, breaking this bond is difficult, and hence this solution is neutral. Now question number 2. 7-bromo-1,3,5 cycloheptatine exists as ionic compound, while 5-bromo-1,3 cyclopentadiene does not ionize even in presence of silver ions. Explained. So for this we should know the structure of the mentioned compound. So this is the structure of 7-bromo. This is this heptatriene. So 1, 2, 3 double bonds, triene, 3 double bonds are there. This is the bromo, this is the 7th position. So this exists as a ionic form. What is this ionic form will be? This is the ionic form. Positive charge, Br negative. Why it is existing in ionic form? Because this is sp2 hybridized after decomposing, and this can delocalize in the empty p orbital of this carbon. So therefore it is following 4n+2 rule, Huckel's rule. It is following cyclic, planar and delocalized pi electrons. Hence it is aromatic in nature. Therefore it is stable. This carbocation is stable. Therefore this can exist in the ionic form. But if you look another structure, 5-bromo-1,3 cyclopentadiene, so this structure will be like this, and if you decompose this one, then you will have this carbocation. This carbocation also have sp2 hybridized orbital. This structure can also show the delocalization of this positive charge like this, but still it doesn't exist because it does not follow the Huckel's rule. If you try to find the n value, so 4 minus 2 divided by 4, so n cannot be a fraction. Therefore this is not following the Huckel's rule, and hence it is not aromatic compound. So therefore it has high energy and it is unstable. Okay, now moving to the question number 20. Write the structural formula of the major product in the following case. So this is the example of Ullmann reaction. When you see the copper and aryl iodide, bromide or chloride, then it undergoes the coupling of the two species. So two molecules of this will couple and you will get this product. This is called Ullmann reaction. Okay, how will you prepare meta-bromoiodobenzene from benzene in not more than 5 to 7 steps? So to prepare the meta-bromoiodobenzene from the benzene, so let's write the structure of benzene and what we have to prepare. Let's write the structure of that also. So this is iodo and bromo at the meta position. So first what we should do, nitration. So if we do the nitration, we know that nitro group is meta directing group. and hence we can bring the meta group. So bromination in the presence of iron bromide will give you this product. So now we have bromo at the meta position. We have to think about how to remove this nitro group. We know that this nitro group can be converted into amine by reaction with the tin HCl to NH2, and after that everything is very simple because we are very familiar with the Sandmeyer reaction. So we can do the Sandmeyer reaction by treating with HNO2 nitrous acid at 0 degrees Celsius to give diazonium salt, and this diazonium salt can be easily break down into by treating with potassium iodide, and then you will have this requested target. Now moving to the question number 22. Give reasons for the following. Aryl halides are less reactive than alkyl halides toward nucleophilic reagents. So we know that this reason of this reaction we know very well because of the partial double bond character through the resonance, which makes this bond very stronger, and hence nucleophile can't break this one. Question number 23. What happens when excess chlorine is passed through the boiling toluene in the presence of sunlight? So toluene, this is the structure of toluene, and the given example is the example of radical reaction. But if you pass 1 mole of the toluene, 1 mole of the chlorine, then you will get only monochlorinated product, and this will give at this position because benzylic radicals are more stable, and since you are passing excess of the chlorine, therefore all these hydrogens will get replaced by chlorine, and then you will have 3 chlorine on this benzylic position. So this will be the correct answer. So this is the all. We have almost solved 100 questions from this haloalkanes and haloarenes series.